Probably live.
Hello, everyone, and welcome to our Ask Us Anything live stream. We are all cosmologists from the Cosmology at Home 2020 conference, and we're here to answer your questions about cosmology. So we have an AMA going on Reddit, the link you can find in the YouTube description, and we'll just go through the questions we get there and answer them. We'll probably not have time to also answer questions from the YouTube chat, so it's best when you just put your questions and comments in the Reddit thread, but we might read that as well. And yeah, let's just start with a few introductions to all the people here. So I'll just go along the list on my screen here. Sean, do you want to introduce yourself and say a bit who you are and what you do?
Hi, yeah, I'm Sean Hotchkiss, a postdoctoral researcher here in Auckland. I have worked on quite a few things within cosmology, from the early universe to the late universe. I haven't been able to stick in one point, but I guess I could probably answer questions on inflation and voids, and maybe ultralight dark matter would be the things I'd probably feel most comfortable on today.
Okay, Ben?
Hey, I'm Benjamin Wallace. I'm a postdoctoral researcher at the Institute for Advanced Study in Princeton, New Jersey, and at the University of California, San Diego. And I'm mostly interested in using the universe as a laboratory for particle physics, and using the cosmic background and all the galaxies that we see in the universe to test what fundamental physics is and what particles there are in the universe.
Tilman?
Yeah, I'm Tilman. I'm a postdoc in Edinburgh. I'm mostly working on the more observational part of gravitational lensing and logical structure observations, which mostly involves a lot of doing statistical analysis on data that other people have produced.
Cool. Robert, do you want to give an introduction?
Sure.
Robert Lilo.
Yeah, I got it alphabetically. Hi, I'm Robert Lilo. I'm a postdoc at the Technion in Israel, and I'm mostly working on the largest scale structures in the universe, both from a theoretical as well as from observational side, trying to understand how they are distributed and how they formed in particular, and what we can learn from that about our theory of gravity and cosmology as a whole.
Do you want to give a short introduction?
Yeah, so my name is
go ahead.
Yeah, so my name is Om Trivedi. I'm currently an undergrad student, but I'm working on inflation, modified gravity theories, and the swarm plan of string theory.
Cool. Alex.
Hi, I'm Alex. I have just started a PhD at the University of Newcastle. My project is mostly studying the large-scale structure of the universe from a theoretical standpoint, and I also do some things with statistics and dark matter.
Okay, Robert Reischke.
So hello, I'm Robert Reischke. I'm a postdoc at the Technion in Israel and at the Open University, and I work on large-scale structure probes of gravity, and as well of dark matter candidates, and I do a lot of statistics. And yeah, if you have questions with respect to dark matter or gravitational lensing or modified theories of gravity, I hope to answer them.
Okay, Valentina.
So, hi, I am Valentina Cesare. I am a PhD student from the University of Turin. I'm working to investigate the dynamics of galaxies in modified theories of gravity, and I'm also an expert in the comparison between observations and the models with the Bayesian statistics. So I hope to answer questions about galaxies.
Cool. And Katie?
My name is Katie Mack. I study dark matter and the early universe and the end of the universe and various aspects of cosmology and particle physics. Yeah, all kinds of weird stuff.
Sounds good. I'm Stefan Hammersheim. I'm a PhD student at the Institute of Astronomy in Cambridge, and I'm working mostly on reionization, so how the first stars in the universe changed it from neutral to completely ionized. And just a quick reminder, so for those who just joined the stream, we are answering questions from the Reddit AMA. The link is in the description. Just go ahead and put your comments in the under the AMA to get your question answered. And let's just start with a few questions that were asking about advice for younger students and undergrads. So we have one question here. Do you have any advice for an undergrad physics student that is interested in pursuing a high degree in astrophysics? How did you discover your specific interest or field of study? Does someone want to answer this question? Ben.
Yeah, let me start with the second part, how I found my passion in cosmology. I think if you already as a child, when you look up in the night sky, I think it's just fascinating that you see all these stars and all the things that are out there. And then if you see these images from the Hubble Space Telescope that tell you that actually what we see is only like a very small fraction of what actually is out there. And then when you start studying physics, you see that in cosmology, all these different areas come together, like particle physics, quantum mechanics, gravity, all these great concepts do fold in. And in cosmology, we can try and really test all of those. So that was one of the main reasons I started pursuing cosmology, and then also drives me forward in my work. And so I think if you're interested in pursuing astrophysics or cosmology as in your studies, just do what you're most interested in during your undergrad studies. Explore different areas of physics, because you'll probably find most of them somehow represented in cosmology as well. So just follow what you think you're most interested at that point, and I'm pretty sure it will lead you to the stars and galaxies that we see in the universe.
Okay, Tilman, you also had an answer to that question.
Yeah, so just from a personal perspective, I didn't actually start out doing cosmology in astrophysics. So I started undergrad doing just physics, then more and more moved into particle physics and did my master's in the interface between quantum information theory and string theory. And then just by chance, talking with people, I drifted more into observational cosmology and gravitational lensing, mostly because I wanted to do something with general relativity. From then more and more moved into data analysis. So where you start off on the beginning of your undergrad says very little where you end up. So yeah, do what interests you and follow your heart.
Okay, cool. Oh, we got one more from Robert Lido.
Yeah, just a small addition, because for me also I had a kind of same fascination for the whole astrophysics cosmology topic, like during childhood, but actually during my studies kind of was more intrigued by particle physics because before I returned. So there are definitely many ways to get there. But like, especially if you want to try that and you count in undergrad, there's nothing that stops you from already trying to reach out to some professor, some expert in that field, ideally at a university if possible, and just ask if there's some possibility for doing some internship, some small research project. I think that's the thing that gets you easiest into that direction, also feel of if that's what you want to do.
Yeah, thanks for the comments. Let's go to the next question. We got one here. We are taught that the universe at cosmological scales is practically homogeneous. But what explains the seemingly chaotic irregularity of the cosmic microwave background? Oh, that's a great question. And does someone of you want to answer? Tilman.
Yeah, I think it's mostly like a misconception, because all the pretty pictures you see from Planck and WMAP, you also know there's tiny blobs. But it's not actually what they measure. If you just point your microwave telescope at the sky, only if you have a very, very good telescope, you only see very homogeneous, like a single temperature intensity all across the sky with no blobbiness whatsoever. If you have a quite good microwave instrument that can measure on the order like 1 part in 1,000, and you see that the sky in one direction is a bit brighter, a bit warmer than the other direction. And just through the Doppler shift of the motion of the Earth around the sun around the Milky Way, and so on. And only if you have a very, very good instruments that can measure the fluctuations on the order of like 1 in 100,000, you see actually these tiny blobs. So all these pretty pictures you see that show the microwave background that aren't just one color, they just subtracted almost all the signal there is just to have something interesting to look at, because looking at just a solid color isn't very interesting.
Great, great. Okay, we have one very upvoted question. Are there any computational barriers standing in the way of better understanding or verification of some of our theories? How useful would 10 times or 100 times more compute power be for your work? I'd also be curious to hear about the hardware and software used for the simulation and any open source packages. So maybe let's start with the first point of this question. If you have any comments, feel free to let me know. I also have a comment on this. So I think there are many fields where we say, okay, we can't do a certain thing because it would just be too computationally expensive. For example, when we want to model, let's say we do some complicated observation of some galaxies or some distribution in the sky, and we want to know, okay, how likely is it that they come from a certain theory? Then what we could do in theory, like technically we could do this, would be to take the theory, simulate everything, and compare that to the observations. And then do this for every variation of the theory and repeat until we found kind of the correct answer. But this is incredibly costly, and there's basically, in most cases, we can't do that. It's just far too costly. But even if we had 100 times more computational power, I think we wouldn't even get close to achieving that. So certainly we would get kind of more details in a lot of things, and we would be able to make bigger simulations. But I'm not sure if we're actually kind of, oh, we just need 10 times more power and we will get a new breakthrough. What are your opinions on this? Okay, not so many computational fields.
Well, I kind of have my hand up because internal Zoom reasons I can't show you. So one thing that I think would be really cool if we had not limitless but just a lot more computing power would be simulating general relativity in the cosmological context in all its full glory. Because at the moment we have to make approximations, and probably in the late universe it's not so relevant because the density the gravitational potentials are relatively small. But if you were to go into the very early universe when the densities are very, very large, and so the gravitational fields can potentially become very strong, it would be really cool to just simulate exactly what we know the equations of motion should be, and how the densities should be changing, and how the curvature of space-time should be changing. And at the moment, either we make approximations or we simulate relatively simplistic scenarios. And then what we might be able to learn from that is more stuff about how inflation, which is this idea for how the cosmic microwave background got so smooth, how that might have gotten started, and how the universe might have evolved straight after it. We still have a pretty good idea about the approximations being valid, but it would be cool to see what things might be hiding if we could simulate that. And the reason general relativity is so hard is just there's so many more degrees of freedom that you have to keep track of than, say, Newtonian physics, where there's just the one potential energy function.
Okay, Katie, you have a question to answer?
Yeah, I just wanted to say about the computational stuff. In addition to improving simulations, as John pointed out, more computing power is going to be super important for observational cosmology in the coming years. So things like giant arrays of a square kilometer of radio telescopes, all putting together their signals to try to learn about the first stars and galaxies in the universe. It's a huge computing problem to get all that information in and to analyze it on the fly and store it and so on. And so big data, things like that in cosmology are becoming very important. So it's not just that's radio astronomy, but you also get that with, I mean, like gravitational wave observations are a big computing issue as well. And then if you want to get into particle physics, there's a whole lot of stuff with like the high luminosity Large Hadron Collider stuff, where you have to deal with just a ton of data and analyze it very, very quickly, and or store it for analyzing later. And the reason that these kinds of things are really important is because a lot of times you're looking for surprises, and so you can't just set up a filter ahead of time to throw out all the data that you don't find interesting. You want to find ways to really get as much out of the data as you can when it comes in, and then store it for analyzing later to look for interesting things.
Alex, do you also have a comment on this?
Yeah, so this is a sort of follow-on from Katie's point, because I actually, in my write-up to this question on Reddit, went and looked up what some of these numbers for this big data actually look like for these next generation experiments. And just for other people to know how ridiculous this is, the Legacy Survey of Space and Time, LSST, is projected to create, let me just find the number. It was something along the lines of 20 terabytes of data each night for 10 years. So yeah, it's a lot. Having 10 to 100 times more computational power would be really interesting. I'm sure we could find a lot with that.
Oh, and Sean, you also want to add a comment?
Yeah, just someone in the live stream has asked a question on this topic. Super interested if there are open source tools you use to perform simulations. The answer is essentially almost all of the simulation tools are open source. We can one of us can write a reply to you in the chat, but if you want to Google things, most of the late universe simulations are done on a code called Gadget 2. I have to warn you, the learning curve will be very, very steep. It's open source in the sense that you can download it and run it, but you're going to spend a long time trying to work out how to run it. Then there's another code would be Enzo or Ramses. I don't know if anyone else wants to chime in with other ones. In the early universe, the codes they would simulate would be, yeah, I'm not going to remember off the top of my head, but I'll look it up. I'll type some answers in the chat for you now.
Yeah, CLASS and CAMP are programs to calculate the cosmic microwave background, for example. And CLASS also has a very nice graphic interface, although it's also a bit tricky to use. Okay, let's move on to the next question. We got a question about dark matter candidates. So we sometimes see particles described as dark matter candidates, such as axions. What are some of the most likely candidates, and why do we consider them more likely than other candidates or explanation? Yeah, Ben, do you want to say something about this?
Sure. First of all, we refer to them as dark matter candidates because they're candidates because, well, we don't know what the dark matter is. It's hypothesized to be there. We essentially need it to explain the observations, but we don't know what it is. And so there are a lot of theories of what kind of particle the dark matter could be consisting of, but we don't know yet. We haven't seen it yet. And so that's why we refer to it as a candidate. Now, as you mentioned in your question, axions are currently one of the most motivated candidates. And the reason for that is that axions were first proposed to not only make up the dark matter, but also solve some other problems that we have theoretically within the standard model. And so that goes by the name of the strong CP problem, if anyone wants to look that up. Another great candidate are WIMPs, the weakly interacting massive particles. And the reason for that is simply that they very easy to understand. And so it's just the easiness of writing down a theory that explains the observations without having to be very elaborate and jump through several hoops to make a model work. So I think accidents and whims are some of the best candidates that we currently have from a theoretical standpoint. But I'm sure other people here on the live stream can add to that.
Yeah, Katie, do you want to add something to that?
Yeah, just to clarify, I don't maybe Ben already clarified this, but when we say we have a candidate, that means it may or may not exist, and it may or may not be the dark matter. But you know, things that we know exist are not the dark matter. I think we can be fairly clear about that. So we're pretty sure dark matter exists, but things that we have measured in some way in laboratory experiments or detected in some other way, generally speaking, we know are not the dark matter. So it's a candidate. So a dark matter candidate is something that's a candidate for both existing and being the dark matter.
Yeah, it's so my comment would be kind of it's more like an idea what it could be, right? So for example, with the WIMPs, we just say, okay, dark matter has to be something that's weakly interacting, is what we say. What we mean with that is basically it doesn't interact with a lot with normal particles, which explains why we can't see it in a normal way. And so it's kind of the idea, and then there are multiple, like the WIMP is kind of one big idea, and then there are multiple particles or models that could be kind of the WIMP. But of course, we didn't find any one yet that actually, well, we didn't find any actual dark matter yet. Any candidate turned out to be true. And while we're on this topic, we got one follow-up questions. Are there any strong alternatives to dark matter or dark energy? And if so, what are they? Does someone want to comment on maybe? Oh, Robert Reischke, go ahead.
Yeah, okay, so it depends a bit on the time when you ask this question, so and who you ask. So for dark matter, or also for dark energy, so let's start with dark matter. So first, why do we know there is dark matter? I think there was also a question like this on Reddit, so I just answered this also. So we know, or we think that there is dark matter because if we look at structures in the universe, then they appear to gravitate much more than what you see with normal telescopes. So there's much more mass than you see, or than you would estimate from the light you see. So if there's not something which does not interact with light, then you, for example, could try to tweak the gravitational law. Right? If you make gravity stronger, then you need less mass to keep these things together, and then this would work again. However, then you need to test this, right? So then we would also, for example, if you would do this everywhere, then gravity would also be stronger on Earth. So that's very difficult to do. So if you want to build a modified theory of gravity, you need to make sure that you modify it in such a way that it only affects, for some reason, these systems we observe in cosmology, so that it only works on very large scales, like galaxies or bigger, but not on scales which are the solar system, because we have tested gravity here very well. So this is one alternative, and this is also an alternative for, or was also thought to be an alternative for dark energy, because if you make the law of gravity different on cosmological scales, it could potentially also act as a form of dark energy. But it is still, if you modify gravity in such a strong way, you need to face it with the observation and see whether this can be the case.
Yeah, Valentina, you're also an expert on this. Do you also want to add some comments?
So yeah, I'm working on modified theories of gravity on galaxy scale. So yes, instead of explaining the dynamics of structures by including a dark component of matter, we can assume that the baryonic matter is the only component in the universe, and we can explain all this deviation by instead a modification of the law of gravity. Actually, we observe, like on the solar system scales, phenomena that are well explained by Newtonian gravity and general relativity. So these modified theories of gravity are interpreted as a more extended theory which recovers Newtonian limit and general relativity in some particular regimes. Taking, for example, MOND, it is a theory that recovers Newtonian gravity in high acceleration regions like the center of galaxies, and whereas it is modified with respect to Newtonian gravity in low acceleration regions, and can, for example, explain the flatness of rotation curves.
Yeah, that's a topic where there's a lot of debate currently in the community, I think. So there are both the ideas of dark matter or of modifying gravity. So that's also something to be stay tuned about for the future. So there might be updates at some point. For the next question, we got the question, is it depressing to study the end of the universe? And I think Katie is the perfect person to answer this question. So go ahead.
Yeah, I don't find it depressing to study the end of the universe. I think it's a very interesting question about the conclusion of our cosmic story. We know the universe had a beginning, and we're pretty sure it's going to have an end one way or another. And so there's this intriguing mystery of what exactly is going to happen. And we have our sort of basic theory that suggests that the universe will continue expanding forever and speed up in its expansion, and the universe will just get darker and emptier over time. And that can be kind of a sad story if you are attached to the universe, existing and being, beautiful and full of things. But it's all very likely to be a very long way off, and so it's not an immediate problem. And I think it's kind of exciting to think about huge changes to the cosmos and ways that the universe could be totally destroyed in various exciting methods. So I find it fun. And if you're interested in learning more about that, I've just written a book called The End of Everything, Astrophysically Speaking, which you can find at any bookstore. It's all about the end of the universe. I have to plug that.
Great. Okay. We got another question. I see many of you are experts on the large-scale structure of the universe. What has been the most recent and most exciting discovery lately for you, considering the structure of the universe? And maybe someone wants to give a quick overview what we mean by structure of the universe, because structure can mean a lot of things, and maybe also point out some exciting discoveries. Otherwise, I'll start with giving kind of a bit of an overview. So what we usually mean by large scale structure is we mean large on the scale of many millions of light years, or well, at least very, very large scales. So larger than galaxies and kind of individual stars, but rather just looking on really large scales. And what we can see is that that the structure follows some patterns. So it's not a completely random structure, but you can see patterns. So the distances between individual galaxies or galaxy clusters follow certain rules, and they are not randomly distributed. But for example, a certain distance is preferred because that's related to the speed of pressure waves in the early universe. And those waves, in a very simple kind of explanation, you could say that these waves kind of form the galaxies today. And that's why the physics of the early universe is imprinted on how the structure looks today. I think Tilman is an expert on this, and maybe you can say a bit more about this.
Yeah, I guess, moving on to what's exciting about this is, so now we have a measure on how the matter is distributed, like in the universe, like the galaxies, but it is quite recent or close to us. But we have other measures on these large-scale structures from very early in the universe, for example, from the CMB. And now you can ask, do they tell the same story? And I think for me, one of the exciting things is if you look, for example, on how clumpy the matter distribution is, then you get different answers depending if you look at the early universe, or the cosmic microwave background, or if you look at the relatively recent universe, where recent here means the last couple of billions of years. So that's recent in cosmological terms. We find that the close-by universe seems less clumpy than you would expect from the much better data from the early universe. And so far, we don't have a good explanation of what's going on there. And that's quite an exciting tension between what's now and what has been earlier. And the resolution of that hopefully should come sometime soon.
Yeah, good point. Robert, do you want to add something to this?
Yeah, I mean, maybe it's not one of the most recent observations, but definitely an exciting one is that what people found is if they looked at like these large overdense regions you find in space where groups of galaxies cluster together, that usually the kind of like the density profiles, like how dense it is in the center and then how it becomes less dense to the boundary, seems to be a very, very universal shape for all these objects that can be characterized by very few parameters. So there seems to be something in the laws of gravity, or maybe even beyond that, that seems to favor all these kind of structures that are bound by gravity. So lots of things orbiting each other to always follow this very similar shape. And while it's very exciting, currently I wouldn't say we have a good understanding of why that happens. We can reproduce it in simulations, and there are some hints at the reason for that, but there is no real insight from not a complete insight from theory on that. But trying to understand better would definitely be a huge step forward.
Yeah, that's good. We have been discussing about exciting observations. Maybe we got one question: what future observation are you most excited about? Maybe like any of you, if anyone wants to add one of their favorite explanations, we can make a quick round of everybody who wants to say something, and go on what you found exciting. Ben, do you want to know? Do you want to say something about this?
Sure. Yeah, I think it's a very exciting time in cosmology these days, because we're kind of in particular in the coming decade, there will be a whole treasure trove of data that will kind of flood all of us cosmologists. There's so many experiments ongoing and planned that we will probably have to really look at specific parts of the data in order to be able to process all of it. And so I think, so just to mention two specific experiments, other people can add to that. There's a huge effort at the moment to measure the cosmic microwave background, this background light that we've already been mentioning here on the live stream, and to really nail the measurement of this background light. And so the two most exciting ones that are coming up in the next few years to 5 years are two observatories called Simon's Observatory and so-called CMB Stage 4, where the latter is essentially all the cosmologists working on the cosmic microwave background coming together and building these telescopes in Chile and at the South Pole to really, as a community, make these amazing measurements. And so I think that's a great community effort that will lead to amazing results.
Okay, I'll jump in with one of my favorite future hopefully discoveries. Those are fast radio bursts. I did only learn about them like very recently, but I watched some very fascinating talks, and they seem to be really exciting. So what a fast radio burst is basically a wave of radio radiation, so kind of long wavelength radiation that's only very short and comes from some very like short event in space. For example, it could be a merger of some neutron stars, or it could be some certain type of pulsar. And these waves, we can use them to measure how the universe is, or how the kind of electrons in the universe are distributed between us and that event. And that's something that was there like for a long time, but we didn't discover them until we kind of changed our searching strategy. And now there are lots of these events that we could discover. And I think this is a very rapidly evolving field. And I'm sure we'll find some great ideas on what to do with those new signals. Okay, then let's go on with the next question, unless someone has missed some comments. Okay. Can you talk about the tools that you use to discover theories about the universe? Oh, that's a good question. Does someone want to talk about those tools? Otherwise, I can start with some of my tools. So I do a lot of kind of simulations try to simulate kind of toy models of the universe, where I try to find out how something worked. So let's say I want to find out how the universe was ionized, right? So the universe was neutral in the kind of beginning, and at some point we know it must have been ionized. So the normal atoms were separated, and we had protons and neutrons flying around. And today we almost see only these ionized things. And our theory is that the first stars that have been created send out radiation that ionizes this hydrogen or the gas in the universe. And then what I do is run simulations. So just kind of take a box of universe basically in the computer, put a few stars in there, and set some parameters. So how fast those stars burn, how much photons they send out, and then see how fast does the universe get ionized. And then see, okay, does this, like assuming this happens, does it work out with our observations? So would we get the right cosmic microwave background observations, the right observations of quasars, etc.? And that's kind of a way to find out, okay, how do stars work? Because, well, how the stars work is maybe a bit too general, but how many photons did stars send out into the early universe? Because as soon as I find the number that kind of works out the best, I know, okay, that has to be roughly the number that is right in kind of the real universe. Robert Reichke, do you also want to comment on this?
So so you covered now the simulation side. I think the other side from a theory part is basically the tools are pen and paper and a trash bin, probably for things which are not so good. But yeah, I think it always starts with pen and paper, and then you try to for example, you want to calculate a certain thing, and then you start calculating this, and you try to squeeze it and massage it as hard as possible until you reach some final destination, you reach a result, or you can't proceed, and then you at some point you might have to rely on simulations, on numerical stuff, and implement actually things on the computer, because you can't proceed any further with your analytics on the paper. And this is basically I think the daily work a lot of people are actually doing, that they're calculating things with pen and paper, and they are implemented on the computer. So this is, or at least it's a lot of my daily work.
Okay, one comment from Valentina. You also want to say something about this?
Yeah, so I use Bayesian analysis, so I do not perform simulations, but for example, to test the theory of gravity on which I work, I compute the model of a certain observable, like, for example, the rotation curve of a galaxy, and I compare this model to the data. And I explore, this model has a certain number of free parameters, so I explore the space of these free parameters, and through a certain algorithm, I found the combination of these parameters which better describes the data. So in particular for Bayesian analysis, I do not find like the best combinations of free parameters, but I built a distribution of parameters which have a maximum, which is the most likely combination of parameters which can describe the data. Instead, in the least square fitting approach, I actually find the combination which minimizes the distance between the model and the observations.
Okay, cool. And Katie, do you also want to give a comment on this?
Yeah, so I just wanted to mention as a theorist, or maybe a phenomenologist is a better term. I mean, I don't come up with new theories, and I don't do observations. I work kind of in between, trying to make connections between those. But the one of the tools that I use most often is other cosmologists. So I think that like we've been in this conference, and we've developed like half a dozen ways of talking to each other and sharing ideas during this meeting, even though we can't get together in person. And the reason that the organizers have worked so hard to put together lots of variety of interactive tools is because bouncing ideas off people and asking questions and sharing information and finding ways to combine expertise and collaborate and test each other as models and so on is kind of the most important thing we do, I think, in this field. And so there is of course a lot of, you know, staring at your computer and yelling at your code and writing equations on chalkboards and scratch paper and so on. But a big part of our work also is just talking and asking questions and sharing our results and so on. So I would say that other cosmologists is one of the most important tools we have.
Okay. Let's go on with the next question. We got one question: why is a CMB usually mapped on an ellipse and not a disk? So the CMB is basically this cosmic microwave background. So this background radiation that reaches us from everywhere in the sky. And Alex, do you want to explain this?
Yeah, I'm happy to take that one. So yeah, the CMB is stands for the cosmic microwave background, which is the earliest light that we can see in the universe. So it was released very shortly after. You know, if you calculate all the way back, it was released in the very, very early universe. And this, you know, is a signal that we get in all directions on the sky. So if you want to, you know, map that sphere onto a piece of paper, you know, just like if you're trying to make a map of the world, you have to choose some sort of projection. And the projection that people tend to use in cosmology is called the Mollweed projection. And it happens to map it to an ellipse. But in principle, you could, you know, map this in lots of different ways. It's just a particular choice that people like to make.
So you could also print it on a globe, I suppose, and then have a real map. Okay. We got one really cool question about the black hole photograph that was made public quite a few months ago. How is the picture of a black hole, which is or was 55 million light years away from us, which is M87, and not a picture of a black hole that's much closer? For example, the black hole at the center of our galaxy, which is Sagittarius, called Sagittarius A star, and is 25,000 light years away, which is the closest black hole from Earth, as the question phrases it. Yeah, I think we have a few hands to answer this question. So maybe Alex, do you want to start?
Yeah, sure. So my understanding of why we have this picture of the M87 black hole, but not the Sag A star, is kind of twofold. So one of them is Sagittarius A star, while close to us, also sits unfortunately in our galaxy, which means there's a lot of stuff in the way. And my understanding is that's kind of the main problem. The other thing that makes it a little bit easier, though, is while the M87 black hole is further away, it's also much more massive than Sag A star. I think it's something like 600 or 1,000 times more massive. I can't remember off the top of my head. And so that both means that it's bigger and also like will be emitting a much stronger signal, even though it's further away. So while it's further away, which makes its angular size smaller, it's also bigger, so that it makes its angular size bigger. So it's not quite as bad as it, you know, initially seems.
Yeah, and at that point, I think the angle to the kind of angular size, the angle of the kind of black hole disk, is pretty much the same for the two black holes, because the one is 1,000 times larger, but also 1,000 times further away, like roughly. So that should.
I think that's about right off the top of my head. I'd have to go and check the numbers, but I think that's roughly true. Yeah.
Katie, do you want to maybe add also something?
Yeah, one of the other reasons that it's hard to see Sagittarius A star clearly is that as a less massive black hole, the stuff going around it goes around faster, and so the variation in the brightness of the accretion disk is faster. And so if you, in order to do these measurements, you have to observe the black hole over the course of several hours, because the Earth is turning and you're trying to put together information from several telescopes as the Earth is turning and fill in this picture. And if the black hole is varying on the time scales that you're trying to do the observation, that it's a much harder problem for putting together the data, and you can't combine the data as easily. And so the cool thing about that is that when we actually do get good imagery of Sagittarius A star, it will be a movie, because the variation will be on a time scale similar to that of the observation, but it's just a much more difficult thing to get a clean picture of this closer black hole.
Oh, that's very nice to know. Okay. I think we got a related question. I've heard that they are actually trying to render an image of Sagittarius A star. Do you know if this is true? Ben, I think you could answer this.
Yes, that is true indeed. So the Event Horizon Telescope collaboration, which put out this amazing image of the black hole that we've just been talking about in the center of M87, is indeed working very hard as we speak on making an image and possibly even a video of Sagittarius A star. Now, because it is smaller, as Katie just said, there's much more things going on, and so they have it's a much harder problem for them to solve than for the image that they released for M87. But definitely stay tuned. There's likely to be some exciting news coming out of the EHT collaboration over the next few months, or as I've heard, at least a year. And it will be definitely very cool to see that, no doubt.
Nice. Okay. We got one space travel related question. So which kind of engine is as powerful to reach a speed of 0.5% of the speed of light? And there are a few ideas. So does someone in the group here want to go ahead and bring up some of the possibilities for kind of futuristic space engines? Maybe while you're coming up with ideas, I'll give a quick explanation why this is actually so difficult. So you might think, oh, just add more fuel, stronger engines, and go faster. One big problem of all kind of space travel and rockets is the so-called rocket equation. I think that was its name, which basically tells you that the essence is, if you want to use more fuel to go faster, you also need to carry all that fuel while you're going faster. So the more, like if you add, let's say, double the fuel, you need a part of this fuel to increase, carry all the additional fuel. So it gets really, really expensive if you want to build a rocket that carries its own fuel. So that's why for really, really fast things like reaching close to a speed of light, you need to come up with new ideas that are not carrying your own fuel. And yeah, I see here there were some ideas of gravity slingshot or lasers or solar wind sails. Is anyone familiar with those? Okay, it doesn't seem that we have so much expertise in.
I know a little bit about some of these things. The solar sails just use. The ideas people are talking about now with solar sails involve shooting a laser at a giant reflective sail and using that to propel a spacecraft, a very, very, very small one. So there's this breakthrough Starshot project that's being discussed, where you'd have a little bitty spacecraft that's like about the size of a postage stamp and a giant solar sail, and then huge lasers on Earth shooting at that to get enough radiation pressure to accelerate this thing. And you could get, in principle, they're talking about getting to like 20% the speed of light over the course of the journey between here and Alpha Centauri. The amount of power, laser power that would take is more than we are capable of at the moment. And the kind of tiny spacecraft you would need to build to do that is not something we can build at the moment either. So that's futuristic, but it's one of the ways. I mean, basically, if you can just get something that constantly accelerates a spacecraft over a very, very long time, you can get to very high speeds. But it's a challenge, especially if you want that spacecraft to hold anything of any reasonable mass.
Okay, Valentina, you also want to comment on this?
Yeah, I'm mentioning an example which I've read. So there is the Breakthrough Starshot project that aims to send a nanoprobe of 10 grams to Proxima Centauri, and it aims to reach it in 4.5 light years, and to reach the stars in this time, the probe will be given a strong impulse with a laser shot from the ground hitting a solar sail, and in this way the probe will reach 15% of the speed of light. So this is the concept of a mission. So as you mentioned, laser and solar sail.
Yeah, that's a cool mission. So for context, Proxima Centauri is the closest star to our sun, and it's already really far away. So even with this super fast rocket, you need a few years. But yeah, that sounds really, of course, a bit futuristic, and 10 grams is not much for kind of a spacecraft. So let's see how that turns out.
Yes.
And we got one question that's also really cool. What is preventing us currently from getting closer than a few 100,000 years to the Big Bang, as far as the background radiation goes? Alex, do you want to answer this?
Yeah, I can take that. So I did, if anyone wants to go and read in a bit of detail, I have put an answer to this in the Reddit thread. But basically, the reason is when the universe was very young, so as we run the cosmic clock backwards, the universe gets smaller, and as it gets smaller, it also gets hotter as all of the stuff in it starts to move around a bit more. And basically, if we run this back far enough, the universe gets hot enough that neutral atoms can't exist, because there's enough energy in the things whizzing about that any electron that's going around a nucleus just gets knocked off, and you just have these charged particles. So if we now run the clock forwards, you've got this hot plasma of charged particles, and at some point the universe cools down enough that you can form these neutral atoms, and at that point the universe becomes transparent. So we get photons traveling through, and that's what we detect as the cosmic microwave background. Before then, because light or any electromagnetic signal scatters off of charged particles, you've got all of this whole soup of charged particles, and the light just scatters all over the place and can't get very far. So the universe is, in essence, opaque at this point. So you can't really get any electromagnetic signal from before the point where everything neutralizes, because the light just can't travel very far because it keeps scattering. So that's sort of the problem there.
Yeah, that's actually a really good connection to the next question, because this problem of only reaching to a certain point is, of course, only a problem of this light radiation. But if you would have, let's say, gravitational waves, you could see much stronger further. And the question we got was, how are gravitational waves detected by LIGO, and how are they traced back to their source? So, Sean, do you want to say something about this?
Yeah, no, I'm not an expert, but I just thought the question was so good that I wanted to flag it up. So they're detected by LIGO because the gravitational waves, being gravitational and gravity being curvature in space and time, you have these big laser beams that the space in between them gets contracted, and you see an interference pattern. Someone else can maybe go into more detail on that, because I thought the really interesting part of that question, because I think there's lots of popular stuff that answers that first part, how they're detected. So someone else here can answer it, or you can find it online. But how do we know where the source came from? I thought was a really cool question. It's really difficult. First of all, if you just had one gravitational wave detector, you don't have that much information about where it came from. You just know when it happened. If you have more than one gravitational wave detector and they detect them, then you start to be able to tell where it came from. I mean, in a sort of super trivial way, if you have one on one side of the Earth and one on the other, and one of them detects it a few fractions of a second before the other one, then you know which hemisphere of the universe it's in. And as you get more and more, you can start to triangulate where it comes from even more. And then if you're lucky enough that when the gravitational wave was emitted, something happened in that location that emitted light. So if you've got colliding black holes and they've got a bunch of stuff around them, or if one of the things that is colliding is a neutron star, then you do get a big explosion. And then optical telescopes that can see light, can see something happening there. And then if it happens close enough in time, you can say that's where the gravitational wave came from. But if you don't have multiple gravitational wave detectors or something happening optically, you simply don't really know precisely where it came from. So a lot of the gravitational wave detections only have approximate areas in the sky where they came from. So that was a really cool question. The answer is, yeah, like sometimes you just can't.
Very nice, thanks. While we're on the topic of gravity, we got the question, why is the gravitational constant a constant? A very good question. Textbooks say that there are scientists who believe that the constant can change, as well as other circumstances, but I've never read it anywhere else. Does someone want to comment on this? Robert.
Yes, so I mean, I think currently the best answer to that, or the most honest answer is, given all the experiment, all the observations we have, all the evidence we have, there's no clear indication for there being any change. So basically it started with, we have gravitational constant already in Newton's law of gravity. That seems to work pretty well on the scales, not only like everyday scales, but up to scales of the solar system without any sign of deviations. And of course, there are also like lab-based experiments to test the value of the gravitational constant. So that's very local. Of course, it doesn't mean it can't change in time. But then if you extend this to general relativity, currently, I mean, given all the evidence we have, there is no sign for it, even throughout the whole history of the universe, to show some change. In principle, I don't see like a super fundamental reason why it couldn't. And I think for the stuff that I've heard of that relates to having the gravitational constant vary is a bit related into the direction of trying to reconcile quantum physics and gravity, where then people say, okay, there are some mathematical frameworks that try to reconcile this by allowing these constants to vary, but this is nothing which that really affects cosmological scales as far as we know it, even if it was true. Anyone wants to add?
Yeah, Alex, do you want to add something?
Yeah, so I thought that was a very good explanation, Robert, but I happen to know that we currently have a bound on basically how different the Newton's constant could have been at the time of Big Bang nucleosynthesis, which is, again, in this period of the very early universe, when these atoms of hydrogen and helium were initially forming. Big Bang nucleosynthesis is our theory that helps us predict, what ratio of, how much hydrogen to every helium atom do you get from our models. And based on Big Bang nucleosynthesis observations, I think the current bound is that at the time of Big Bang nucleosynthesis, Newton's constant has to be within about 10% of its current value. So that places some sort of definite bound on how much it could, have varied since then, I think.
Okay, very good. Let's continue with one question on gravitational lensing. In some cases, it's very obvious. Okay, yeah. So on gravitational lensing, sometimes it's obvious what's happening, but otherwise, how do we know we are not being fooled, seeing some object that isn't there? Also, if we use nearby galaxies or structures to determine whether an image could be a result of a gravitational lensing, how do we know that our perception of those nearby objects isn't already flawed by the same process? That sounds an exciting question. Does someone want to answer here? While you're thinking about answers, I'll just give a quick introduction to what lensing is. So one of the things that follows from Einstein's general theory of relativity is that mass or some matter and energy in general curves space-time. And this has lots of effects and is quite not completely trivial. But one effect that it has is that when light travels close to, let's say, a galaxy or some other massive object like a black hole, its path gets bent. So it doesn't travel on this straight line on the kind of simple view, but it actually travels through a straight line, but the straight line goes through kind of a curved space, which is why it appears to be not straight, but kind of go in a curve around some object. And this effect we can use to find out all the matter in the universe, because all matter causes this deflection. So whenever we see the deflection, we know there must be, well, it's some matter. It's kind of the simple explanation. Katie, do you want to go in a bit of say something about this?
Yeah, so with an individual lens, it's sometimes there's some ambiguity between a weirdly shaped object and a lensed object, in the sense that what we're seeing is the light. We're seeing some shape of some distant galaxy that's distorted by the lensing object. There are a few ways we can know if something is a gravitationally lensed object if what we're seeing is, you know, the distorted picture rather than just a weirdly shaped thing. One is if we see multiple images of the same object. So we often see that where we see multiple images of the same galaxy sort of distributed in a particular pattern that you would expect for gravitational lensing. One is if you see just a really wild distortion, like an arc around some massive object, and that ends up being clear. But in a lot of cases, we use what's called weak gravitational lensing, where there are just very subtle changes to the orientation of the images of galaxies. And if you have enough of these, and you can see you have, you know, hundreds of galaxies in the same picture, distant galaxies in the same picture, and they're all on average tilted a little bit in a particular direction, then that can tell you that that there's this sort of weak lensing going on in a statistical sense. And so you can measure the mass between you and those distant galaxies sort of just on average. And in that case, for any individual galaxy, you don't know if it just happens to be oriented that way or if the image is tilted by gravitational lensing. But by adding up a whole lot of these, you can get an idea that there has to be something that's doing the lensing for the whole field.
Yeah, that's very, very nice. Tilman, do you want to give a bit of context to that as well?
Yeah, so specifically on the last point, so yes, the easy picture is as all your galaxies are randomly orientated, and if you average over all of them, then the orientation average out, except for the lensing signal that you care for. But by now we're getting so good data that it actually matters how these galaxies are like intrinsically orientated. And these are subtle effects. So if you have a galaxy that sits close to the big amount of mass in the foreground that's causing the lensing, then that big mass can also, just through gravitational effects, can affect how galaxies around it are oriented. Or even galaxies that are further away that look like they are lensed because they're aligned in the same direction. The alignment can happen because they're interacting gravitationally, because they're close by in a sense. And that's a small effect, but it's one of the most importantly for big gravitational lensing surveys. And the problem is it's very poorly understood because it's not clear what kind of galaxies align and how they align. So that's one of the big modeling questions that we have to deal with in what might look like gravitational lensing, but is actually not.
Okay, it looks like, Sean, you also want to add something to this.
Yeah, just wanted to mention something known as kind of time delay in lensing. So it was mentioned that you can have multiple images of the same thing, but the time it takes the different images to get from the source to us, if they take different paths around the lens, can be slightly different, which is really cool because it means that if you have a telescope that's taking images quickly enough, you can actually see that one of the images is slightly ahead of the other one, which is, I mean, that's kind of cool just on its own, but it also allows you to learn about the distances that the differences in distances that those two light images, the paths, have taken, which has some really cool consequences to do with measuring how far away, say, the lens is and other things like that, which gets into measuring of cosmological parameters like the expansion rate of the universe, which may or may not be causing problems in the standard cosmological model with different measurements giving different values of the expansion rate. So tying into the original question of how do we know that it's actually been lensed, if we can see that it's the same image, that means that it is being lensed and it's not just funky, but it also allows us to do this extra interesting stuff.
Yeah, that's a good point. And I see this was a really good question because we got another comment from Katie on this question.
Yeah, I just want to follow up on Sean's thing. There's a really cool example of this time delay thing. I think the lens is called the Revstall lens or something, where there was a supernova seen in one image of a galaxy, and then the observers who saw that figured out that what the time delay would be for another image of that galaxy, and worked out that in something like a few months to a year, you would see the supernova again in the other image, and that happened. So they were able to see the supernova, the same supernova, go off twice, separated by something like 4 months or to a year, which is very cool to watch a galaxy where that star still exists and then see it blow up. So I mean, you couldn't actually look at the star. It wasn't quite, we didn't have that good a picture of it, but it's very cool that we were able to do that.
Okay, thanks. I see one question that here from Reddit, from the Big Bang. How do we know, like, how the elements that we get from the Big Bang, which is just hydrogen and helium, how do they create the solids that we need to form a body like a planet? And I also see that Haley just joined the stream. So welcome, Haley. And do you maybe want to give a short introduction and maybe also answer the question while you're at it?
Sure, I'd love to. Hey guys, sorry I'm late. My name's Haley. I'm a postdoc in Cambridge in the UK, and I mainly worked on doing cosmological simulations, and I work a lot in general relativity as well. But I'm going to give a go at the formation of the elements. So this is really fun. So as Stefan just said, like in the early universe, we only had really simple elements like hydrogen and helium. And basically we just had like a giant kind of soup of hydrogen and helium, which like regions which were like a little bit hotter than other regions collapsed to form like even more dense regions. And eventually you get to such a density that you can form a star, which becomes hot enough so that it can start fusing these elements together to make other elements. And then when these stars go through their life and explode, they kind of shoot out all of these new elements that they've made through fusion into the universe. And then those elements go on and continue this process for a few generations. And then that's how we end up with the kind of complex elements that we see in like planets and in ourselves and all that kind of stuff. So it's all gravity and a bit of heat as well.
Oh, very cool answer, thanks. While we're talking about the Big Bang, we have a question: can we tell, or do we know where the Big Bang happened? Is there a center of all the expansion? Sean, I think you might want to. Katie, go ahead.
Yeah, the Big Bang happened everywhere. There is no center of the universe. There is no center of the Big Bang in the way that we understand it. What we know about the Big Bang, when we talk about the Big Bang theory as cosmologists, what we're really talking about is the fact that the early universe was hot and dense and filled with sort of roiling plasma. And we know that because we can see that, because we can see the cosmic microwave background, which is the light from that glowing early universe coming directly to us from the most distant parts of the universe, where it's taken 13.8 billion years for that light to get to us. And so everybody, like every part of the universe was hot and dense at the beginning from what we know, and every part of the universe is expanding away from every other part of the universe. So the universe might be infinitely large. It might have always been infinitely large, and there was a time when it was much more dense and much hotter. but there's no point from which everything else is moving. Everything is moving away from everything else. Everything was hot and dense in the beginning. And when you go back before that sort of fireball stage, there are various things that could have happened that some of them might have involved a singularity, but a singularity doesn't necessarily mean a single point. It just means sort of infinite density, and it still could have been an extended space. So that gets quite complicated. But in any case, all of space was in that really dense space, this really dense state at the beginning. So it's very counterintuitive, but as far as we know, there was no center of the Big Bang. There was no center of the universe. And every point was in the Big Bang, whatever the Big Bang was at the beginning.
Yeah, that's a very good answer. We also got a similar question about the size of the universe. And that's also mentioned that if the universe started from an infinitely small point right after the Big Bang, then no matter how fast the expansion rate or big the time scale, it will never go to an infinite universe. But doesn't this contradict with other things? And yeah, I think that's the point you're making. Basically, it doesn't have to be a point to be infinitely dense. It could just be infinitely dense everywhere or in some region. That is our observable universe today. Yeah, that's very good. For the next question, let's go back to gravity again. Does the gravitational constant have any meaning in GR, so in general relativity? Robert, do you want to talk about this question?
Yeah, I'm happy to. It does for the following reason. So it just first of all, it just tells you how strong matter or any energy couples to the geometry of spacetime. Because so in general relativity, we use the geometry of spacetime to describe gravity, and the gravitational constant exactly tells you how strong any matter flow or any energy you have in your spacetime couples to its geometry. So there's a direct meaning to it, right? And you can actually there are actually mathematical theorems which under certain conditions tell you that in general relativity you have to have this coupling constant, but you also can have another coupling constant, which we in cosmology happen to observe to be something which drives the accelerated expansion of the universe, and which we call or would call a certain type of dark energy. So the gravitational constant certainly has a meaning in general relativity, especially since the Newtonian theory of gravity comes out in certain limits from the general theory of gravity. So when it has a meaning there, it also has a meaning in the general theory.
Yeah, that's a cool answer. We'll just take another question from the live stream. And that was, as computational power is made cheaper and more easily available, what kind of exciting possibilities lie ahead for both theoretical and experimental physics that simply weren't possible in the past? And we discussed a bit about this in the beginning, but now that Haley is here, maybe you want to give a bit on how you simulate numerically general relativity and how this will help you.
Yeah, sure. So, I mean, my answer is probably not so much about what lies ahead in the future, but it's more kind of like some exciting developments over the last 10 or 20 years, which is just totally unfeasible in the past. So it's kind of applicable, but I'm going to go for it anyway because I think it's cool. So I'm a bit biased on this, but I like general relativity a lot. Those people who know anything about Einstein's equations will know that they're really long and complicated and really, really difficult to solve. And it took a very, very long time for anyone to be able to write down any kind of solution to the equation, any kind of exact solution to the equations that was useful. So what people have done over the last 50 years or so was develop numerical techniques. So what this means is just gives us a way to write a really complicated set of equations in a way that a computer can solve it for us. So we don't have to do it on a pen and paper. And so this lets us do simulations of a lot of relativistic things that we literally can't solve by hand. So these are things like black holes and neutron stars. So they've been really useful for gravitational wave searches. And we just physically did not have the computational power to do this properly until about the early 2000s. So this is a really recent development. And ever since our computers have got powerful enough, this field has absolutely exploded. And it's basically the reason that we know a lot about gravitational waves, because all of the gravitational wave signals that we see are directly compared to numerical relativity simulations. And so these are really, really important and really useful for us to figure out what kind of black holes we're actually seeing. And I'm particularly excited because I work in numerical relativity and I apply it to cosmological simulations. So this is a different way to look at the universe. And with this kind of increase in computational power, this is really exciting for people like me who want to study the whole universe in numerical relativity. So yeah, I think it's really exciting.
Great, great. And I think we have one very exciting question from the Reddit AMA here, because 3 people already told me they want to talk about this. So the question says, sorry if this is stupid or has been asked before. No, it's probably not stupid at all, because we got lots of interest here. There are no stupid questions in general. If we combine the data from the cosmic microwave backgrounds, from the observations of the large-scale structure of the universe, and the theories of inflations, does everything add up together, as the 3 things seem to be related, or are there discrepancies? So who wants to go first and talk about this question? Robert, do you want to start?
Oh, I can start, yeah. So, so the different data sets we have are usually analyzed all together, and with different models of complexity. So there we have something which we call the standard model of cosmology, which is a model which has certain parameters which are then fitted basically to the data. So you try to find the parameters which explain the data best. But then you also need to check whether these data sets are also consistent between each other, because it could be that if you fit all together, you find some set of parameters, but if you just take one data set and you fit the parameters to it, you might find different values, which are actually way off of the parameters you found before, of the values you found before. And this is how we check this, and this is what this discrepancy means. So I think the general picture is that all observations fit or are fitted by the standard model of cosmology reasonably well, though there are some discrepancies, small discrepancies, which are under investigation at the moment. And I think I give to someone else, because a lot of people want to talk here. Tilman raised his hand, for example.
Yeah, go ahead, Tilman.
Yes, so in general, our standard model of cosmology fits extremely well. So it's hard to come up with something that fits better. Or better in a statistical sense means it isn't just adding more and more freedom. So you always want to include Occam's razor. So any more complexity you add here to model needs to create a much better fit. In general, all the data we have is extremely well fit by just the standard model. There are subtle differences in certain parameters. So for example, if you look in the low redshift universe at supernova, that are calibrated like basically starting from the Milky Way and going further and further, then you infer an expansion rate that's like 10% higher than what you would infer if you start way back at the CMB. Or for just logical structure, like how clumpy is matter. If you look at how clumpy matter is through lensing, for example, the value you get there is about like 10% lower than what you would get from the CMB. And then you can play a lot of statistical games and trying to quantify on how well these discrepancies or how large these discrepancies are. And that's actually quite a complicated problem, because you have a lot of parameters, usually the 5 to 6, that describe the whole universe, which is an amazing thing in itself. And then one of them is slightly different in one probe than in other. And the question is, do you just look at this one parameter and then you might think that can only happen 1 in 1,000 times? But if you were to look at all the parameters, then that discrepancy shrinks, because if you have one outlier out of 5, that's a lot more probable than if you just have one thing you're looking at. So summarize, yes, if you look at it holistically, I think everything is looking fine, and it's incredibly hard to come up with something that's more complicated that works better. If you want to nitpick on specific parts, then there are interesting things going on because things don't work completely fine, but I mean, that's science. That's the exciting thing. That's why you're here.
Okay. Let's take another question from Reddit. How will the concept of dark matter and dark energy shape science in the future? Is it possible that we would abandon this theory, or is it solidified at this point? Yeah, Katie, go ahead, and you want to answer this question.
Yeah, I think one thing that dark matter and dark energy will shape in the future is the entire cosmos, because they are by far the dominant components of what the universe is made of, and they entirely determine the evolution of the cosmos from here on out, and indeed from the beginning to now. So, or at least dark matter and dark energy wasn't that important in the beginning. So I think that they're the big questions, right? They're the big things that they're most of the universe. They're 95% of the universe, and we need to figure out what they are. And if we do figure out what they are, we will very likely be much closer to understanding physics in general. So, particle physics, particle physics doesn't currently include dark matter as far as based on what we've detected and what we really understand. So if we figure out what dark matter is, we'll have an idea of where to go next with particle physics. Dark energy might be telling us something about quantum mechanics. It might be telling us something about general relativity. So if we figure out dark energy, then we might have a better shot of understanding all of those things. So I think that they are the biggest questions in cosmology, both in terms of the biggest things in the universe, dominating the universe, and in terms of what we can learn about physics and the universe in general. And I think we're pretty confident that both of them exist, because in the sense that they fit the data better than anything else. So we gotta kind of understand what they are, or if there's some model that comes up that fits the data better than dark matter and dark energy, then we'll go with that. But at the moment that doesn't seem to be the case.
Yeah, that sounds exciting. Owen, do you also want to add something to this?
Yeah, like just to add to what Katie said, the one thing that might be a bit more kind of like a make or break for many theories is the kind of measurements that will be done on dark energy and dark matter in the future, the more precise measurements, to be honest, because there are like nowadays we are having loads of theories on modified gravity or like general cosmology and stuff like that, and the best way to test out whether those theories will be compatible with some possibly good theory of quantum gravity is through measurements on dark energy and dark matter. So I think in the future, we might be able to rule out loads of theories on the basis of whatever precise measurements dark energy and dark matter tell us about them.
Okay, yeah, very good. Let's go to the next question. Is there any chance that the redshifted galaxies we see are not so much moving away from us, but rather something is happening to the light itself over the extreme distances? Could that account for further galaxies being more redshifted? And that sounds like a very good question. I can say something about this, unless someone else wants to go. Yeah, so one thing that we observed so let me explain a bit about what redshift is. So when you look at the galaxy, you see kind of a certain color, and you don't really see a color, but you see kind of a spectrum of light. So you might see kind of, it's broadly kind of this color, and then it might have some lines, like some specific wavelengths, where there's a lot of radiation from this wavelength. maybe because there's some atom that has a certain transition that enhances this frequency. And kind of using this color in the spectrum allows you to see, well, it allows you to notice if the spectrum is shifted to the left or right in frequency. And what this does kind of in practice is, the further away, if the galaxy is moving away from us, it looks kind of red. And if it's moving towards us, it looks kind of blue. Of course, this would be very exaggerated. So actually, in reality, the effect, especially like in what we say blue shift, isn't necessarily that the galaxy looks blue, but it's kind of the spectrum is shifted into the blue or towards the red end. And what astronomers and cosmologists found out is apparently galaxies look the redder the further away they were. And that kind of led to the theory actually of that the whole universe is expanding and that kind of space itself grows and grows. And because this exactly would tell you that the further away a galaxy is, the faster that it is moving away from us in that sense. Yeah, Alex, you had your hand up for a second. Do you also want to comment on this? Because I think you might explain this better than me.
Yeah, so this is actually a really good question because I think it was in the 1920s or 30s. This was actually basically an entertained idea for explaining the observed data. So this was an idea called tired light, and it's important to try and think of these sorts of things. So if your only measurement is galaxies that are further away from us look like they're redder than normal, then there are lots of different ways you can explain that. But this idea isn't really entertained anymore because we have lots of other data now. And this tired light idea makes some other predictions, I think, in particular about like the surface brightness at different distances or something that don't match with our observations, but that the expanding universe does explain. So it's a really good idea. This is something that was entertained, but it no longer really fits with the data that we currently have.
And Sean, do you want to add something to this?
Yeah, I mean, and the tired light hypothesis also kind of predicts a roughly static universe throughout history, right? Like it's redshifted because it is further away, whereas it doesn't fit particularly well with a kind of Big Bang idea. And the Big Bang made lots of predictions about, first of all, the cosmic microwave background, second of all, that it would have anisotropies with the same statistical structure as the density contrasts that lead to galaxies, and all of these sorts of things that subsequently got observed. So it would just start to get very, very intricate to try and explain all of those other things with some other new physics, and then have tired light explaining redshift. Whereas the idea that it's an expanding universe led to so many predictions that subsequently got observed that it just becomes it's a much more simple model that encompasses everything.
You just mentioned that the Big Bang kind of predicted the cosmic microwave background. Do you want to expand a bit on this? Because we also got a question, why is the CMB good evidence for the Big Bang?
I could. I mean, we were originally planning on going for 90 minutes and there's 2 minutes left. So at some point we need to think about the summary stuff. And this might be quite a long question, but okay, if we think the universe is expanding now, which is essentially saying that there's a Big Bang, if we go backwards in time, eventually the density reaches a very, very, very large value. So if you follow what that means, it means that as you go backwards in time, everything's getting hotter because things are getting more dense. Eventually, the universe, going backwards in time again, would get so hot that hydrogen would not be atomically stable. The electrons would have enough energy to escape the protons. So, okay, we've gone backwards in time. Now let's start going forwards in time. We're in a universe where it's so hot that we've got, instead of neutral hydrogen, we've got a hydrogen plasma. We've got a bunch of electrons and a bunch of protons not bound to each other. Now we go forwards in time. We see that at some point in time, the universe will cool enough that it becomes stable. And as soon as it becomes stable, instead of having a bunch of free electrons, which would block light, because light is electromagnetic wave, it'll interact with the free electrons. As you go forwards in time, once the hydrogen becomes stable, it also becomes transparent. And because it's making up most of the visible stuff in the universe, at that point of time, light is able to freely travel and is no longer interacting with these free electrons. So at that point of time, the energy would have had roughly the same energy as the same energy you get when you ionize a hydrogen atom now. That's not microwave radiation, but that happened a long time ago. And as the universe expands and cools, that particular radiation, when you observe it today, is in the microwave frequencies. And so this is what we would call the cosmic microwave background. And so there's no other reason that a particular, the sort of background light in the whole universe should have that particular frequency and be homogeneous if you have other models. But in the Big Bang model, it was predicted that it should be there. I also mentioned anisotropies, which I guess one could go into, but maybe we can save that for another live stream, another week perhaps, or one of us can write it up in the Reddit AMA.
Yeah, great. You reminded me of the 90 minutes that are already over. That was a really fun 90 minutes. So thank you all for sending the great questions, and thank you all for the people that are here to answering all those great questions. So that was a lot of good questions. There are still some questions on Reddit. We will be answering for the next few hours, I guess, more of the questions on Reddit in text form. If you have some unanswered question, we might get to that as well. And yeah, we might repeat this maybe next year when we have the next Cosmologic at Home conference. Maybe Sean, you want to comment on this?
I've changed it to gallery so we can all just do a wave as we say goodbye. There'll be a conference next year, so stay tuned for next year. I'm sure lots of us will be doing outreach in the meantime, and our social media is in the Reddit AMA if you want to. I mean, Stefan does a weekly, I don't want to just sort of dump you in it, but you do a weekly live stream that people might want to catch.
Next Monday on this channel.